class. Just now, this should kind of tell you when you, and today when we put one into the other, you're going to see the difference. But we're going to put one into the y, and there's your square. So yeah, we're looking at a parabola. Just keep track of your orientation. Try to see where it starts, where it ends. I gave you all the -5 to +5, just as a good starting point to go through that. And then these guys, there's another t-squared. Your time, you're going to see some of it looks like a point, and it doesn't look as round. Did you notice that? If you set your time differently? You know, just to play with it. There's no set thing for that. When we use the applications, we'll change that. We'll change that a little bit. And then this one too. Everybody's good with that? Okay. Now today, we're going to eliminate the parameters algebraically, and we're going to find what we call a rectangular equation. A rectangular equation is just a y equals x and y equation. You're going to see your ellipses come out. You're going to be able to graph your ellipses using your parametrics. You can do that using the y equals. So today we're going to eliminate these things algebraically. Okay. All right. If you could add one thing to your notes. It says solve for t in one equation, make that save your x equation. All right. I might have changed it and never saved it, and when I printed out your things like these are your student notes, I might have not put it in there. And you're going to substitute this into the second equation. Your result will be 1y equals equation. Because don't forget, you get an x equals, you get a y equals. So if you work, and each one of them contains a t somewhere. So if you solve it in place of t, and then replace it with your x, you're back to a y equals x equation. And that's what you can graph in your regular y equals. We call that a rectangular equation. You're going to see your ellipses come out of this, your circle come out of this. We're going to work on those. I'm going to hold this one off for a second and just go to number 3 in your homework. You have two equations. So your goal is to solve the first equation in terms of t. Okay, solve for t. So obviously this one is already solved for t. Let's say it said t plus 1, then I would say subtract 1, x minus 1 equals t. So I'll do that. So say it says this. Solve this for t. So just subtract 1. Now, you're going to substitute this into the second one for t. You're going to eliminate this parameter. We'll graph this parameters, and we'll graph this y equals. So if I substitute this in, and then you'll see the equation of your line come out. Here's the equation of a line. So if I put this in my parametric mode, I'm going to go to my y equals. I'm going to put in, what did I say, t minus 1, t plus 1. And then this was negative 2t. So when I graph this, I get a line. Is this line crossing at the positive 2? looks like a -2 slope, right? So this line, and now when I go back to my regular mode, my rectangular mode, and I put this in, this was -2x. Okay, hang on. This gives me the same line. That's my rectangular mode. Okay? So we're substituting one to the other. So you didn't get that graph? All right, take a look at your windows. What do your windows look like? Are you in parametric? It's just your window. Okay? All right, so now we're going to take one that's a little bit messier. A little bit messier. Now, first thing we have to worry about is the domain restriction. Because we've got a radical and we have a denominator. So back to our domain restrictions. This guy says, what's my restriction in a fraction in the denominator? T can't be -1 because if I set this equal to 0, because it can't be 0, so T cannot be -1. Okay, so this guy, it's a radical under a fraction. So I take this little thing out and I say this must be greater than 0. Normally a radical underneath it has to be greater than or equal to 0, but because it's a denominator in a fraction, it cannot be 0. So T is greater than -1. So T cannot be -1, but it can be greater than -1. So my domain says -1 to infinity. And when we graph this, we're going to have to look at this because, again, you'll see it when we go to graph this. I did copy the two graphs down here so that you could see the rectangular one and the parametric one, so that they would be the same, just so that you get a feel for it. Now, we're going to take your first one and solve in terms of T. Any suggestions? Square both sides? Let's square both sides. This you can square. It's a monomial. If it's a binomial, then you'll have to, distribute it out. But this you can square. Yeah, we can cross multiply. We can also take a little shortcut. We can cross multiply this. We can also take a little shortcut and flip these both over, if you like. But we can cross multiply. So we're going to distribute. It is weird.
I like that.
It's okay, we'll get there. So now we're gonna solve for T. So T is over here. So get this guy by itself. That's x squared T plus x squared. Just distribute this. My T's don't come out good when I write sideways. Sorry. So just move this x squared over. We're just solving for T. Divide by x squared. Which we normally don't do, but we're doing it. So it's going to give me 1 over x squared minus 1. This is probably the worst one you'll see. It's got fractions, it's got a complex fraction.
Why is it minus? Yeah.
Because x squared over x squared is 1.
Yeah, but can't you not,
Separate, yeah, well, separate this. Come on, separate it. What is x squared over x squared? 1. You can take a shortcut here. You could flip these over. And then, x squared. And then cross multiply there. To do that. But we're fine here. Alright, so now we're going to take that. You're not going to like this even worse. But we're going to substitute in for T. Both T's. I know, it's not pretty. Huh? Well, it made sense on the other one, didn't it?
I understand it, I just don't like it.
Oh, I know you won't like this.
Yeah, no.
But this is like worst case scenario. This is not, if I gave you I gave you a simple one, but when you do the hard ones, you'll say, well, how does that work? So we're doing a hard one. All right, so now we're going to substitute in for t. T is, hang with me, guys. Did that say plus one? Plus one. Hang in there. Not so bad. So now, in the denominator, we can cancel out your ones, right? So we're left with complex fraction, but that's okay. What's our common denominator? X squared. I'm going to put x squared on the top of every term. This is an easy one, actually. X squareds come out. 1 minus x squared over 1. So what does this look like to you? 1 minus x squared, what does that look like it should be? A parabola. And which way is it going to open? Down. And I can't move this right now, but yours has the graph on the bottom. Doesn't it look like a parabola that opens down? But why did I stop short right here? Why does it stop short right here? Because of your domain restriction. Well, this you'll see it better on this one. Even though it's greater than -1, it kind of stops short. My time is off on this one. My whole board is off. Okay, so that's probably the hardest one that you're going to see. The homework starts out easier, and I don't think you have too many difficult ones in there. Not too many difficult. I don't even think they gave you a fraction. Only one of them, number 11, has a fraction in it. The rest. Oh, those will be even easier. Okay. So just remember, just follow those simple directions. You're solving for t. You're solving for t. You're plugging it for, in terms of t, you're solving it, plugging it into the y. Now, the only one that this plays around with, using the curves, and this is where you're going to see your ellipse and your circles come out. We just have to play with your window a little bit when we graph this, but we will in a minute. So what I want to first do is graph this using a parametric and see what this looks like. So pull up your calculator. We're gonna play with this first. Go to your y equals, and you're gonna put those two things in. 3 cosine, just put it in, bless you. When you hit this, it's gonna say t, because your angle now is your parametric one, and that's fine. Just leave that in there. And what is the next one say? 4. It's going to have a t in there instead of an angle, because that's where your third.
Should our mode be in degrees?
We're going to move that in a second. Okay. We're going to have to change your mode, make sure it's degrees, if we do degrees, and we're going to have to change your window. So, everybody has this in. Your angle is going to come out as your t, because you're in your parametric mode. It's not an x, it's not an angle. Well, it is an angle, but it's in terms of t. That's the thing that's changing. Your angles are moving around in a circle. So remember, your parametrics say you got a third thing going on, and that's what's moving us around is our angles. Now, hit mode, make sure you're in degrees. We're in parametrics, we have to be in degrees for this. Now, in your window, if you start your minimum at 0, your maximum has to complete a full circle. So your maximum has to go, because our t is our angle now. So our maximum has to go to 360. We'll graph it and then we'll change it and stop it, and you'll see what happens. So right now, I just want you to get the right window in. Now, because your t is in degrees, your t step also is in degrees. Picture this. If I have a circle going around, as it goes like this, it's going by angles, like a clock. Like picture your clock, your hands going around. Picture your hands like going every 30 degrees, every 60 degrees, every 90 degrees. it's going around in a circle. So I have to complete 360, and my T-step now will be in angles. So just set your T-step every 30 degrees. And we'll play with that. We'll change it. We'll make it a little higher, a little lower. You can leave the rest of these. The rest of these go by where your radius falls. And I don't think your radius is that big.
I looked at the step as like what it originally was, and I was keeping forever.
Oh, yeah. Don't leave it as original, because what you're saying is 0.5 degrees. So if you say 0.5 degrees, this thing is going to go so slow, it's going to go every half of a degree. That the angles work very differently than this. But that's okay. You're getting a feel for this on your own, which is what I want you to do. So now just graph. See your circle go through? It started right here, right? I want you to keep track of where it started. Now say I didn't catch it. If I hit graph again, nothing's going to happen. So just go to your window and change this. Maybe I'll change this to 20 so I could see it a little slower. So see, I started right here and it came all the way around. So when you do this, you're going to do this. You're going to start it here and you're going to show me orientation. I got to reset my board, sorry. You're just going to show me orientation. Now, it might look like an ellipse here on your calculator. Just do a zoom 5. On your regular screen, it's a little oblong in one part. It's a little exaggerated. So if you do a zoom 5, you'll get a better circle. This one's coming out fine, just in case you came out crooked. Now,
Zoom 5 looks less like a circle.
Yeah, Zoom 5 looks more like an ellipse.
it looks more like an ellipse?
Mm-hmm.
Oh, so maybe this is an ellipse. This is an ellipse, because these are different. So this is an ellipse. So zoom 5, and you'll get a better feel for what this is. This is an ellipse. It's just they're close. 3 and 4 are very close. So it's close to a circle. So a zoom 5 will give you a little bit better feel. Now, play with your window a little bit.
I changed the T-step to 60 and it made a hexagon.
Okay, so now it's not as smooth, right? Because every 60 degrees, this is what's happening. It's going 60 degrees, making a dot, 60 degrees, making a dot. It doesn't have the continuity in between. So Lily did this and it made a hexagon. Because every 60 degrees, it's putting your mark. So it's not counting the ones in between. Now, watch what happens, guys. If I change this, watch what happens if I don't go to 360. Say I go to 180, what do you think should happen?
This is so fun. It's gonna be a
I should get,
It's gonna be a line.
well,
Nothing we have.
180 is half of your 360, right? So I should get half of my circle, my ellipse, actually. I should get half of my ellipse, right? Now, you were never able to graph an ellipse in your y equals, right? You had to separate it and do square root and take two things, but now we're able to do this. So kind of play with this a little bit. Your x min and your x max and your y min and your x and your y max just go by the bottom of your, when we convert this, either it's a radius or the bottom of your ellipse when we do this. So that you can just leave that at 5, 10, whatever you want to leave it at. Sometimes your calculator resets it because it's not sure exactly what you're doing, so your calculator can reset these. But try to, play with this a little bit and get a feel for where this is going. And again, sometimes you have to play with your T-step a little bit. All right, so let's just take this and convert this. So I'm converting these. So here's my equations. I'm going to solve in terms of my tape, my parametric. So I just got to get rid of this 3. And I just got to get rid of this 4. Okay, now, in terms of a circle, an ellipse, anything else, anything dealing with a cosine and a sine, there's one identity that you had to remember. That was this identity. Cosine squared, yep. This is the one thing that's going to help us convert this into a rectangular equation. So we're going to take the cosine of this angle. So technically, you can leave it as an angle or you can put it as a t, whatever you like. replace this in here. But don't forget to square it. And we're going to replace this in here. And don't forget to square it. So we get x squared over 9 plus y squared over 16 equals 1. And what is that an equation of? Not a circle. Ellipse. Ellipse. That's an ellipse. Right? That's your ellipse. This is the one identity that you have to remember for this. What do I know that deals with sines and cosines that gives me back to one equation? Sine squared plus cosine squared equals 1. Now, sometimes you're going to see, like it'll say minus 1. So when you add 1, it's going to say x plus 1 over 3. Isn't that where your center comes from? Your offset center? So if this has anything else out here, move this over, keep this by itself. Look, this is it. This is the equation of your ellipse. A is 3. Oh, sorry, A is 6. There's 4. B is 3. That's why it looked so close to a circle, because these were so close. Okay? Now, let's do one quick circle one. And the circle one, again, you're going to do the same thing with your windows, so your windows should be fine. God bless you. So your circle, you do have to remember these two setups. But it's not so bad, because isn't H associated with the X? Isn't K associated with the Y? So this is not too bad. X is associated with my cosine, Y is associated with my sine. So now, we have to have some information. This is my HK, this is my R. Radius. We're doing a circle, so the only really thing you ever know about your circle is the radius or diameter. So, okay, so we're going to take these and put them in here. We're going to make two equations. The H is negative 3, plus my radius, cosine theta. Then my Y is my 1 plus 3 sine theta. This is where my parameter goes, right here. You can put this in your parametrics, and I put it in here. Did I graph it for you guys? So put this in your parametrics and graph it. Use your same window. Use your window, make it go from 0 to 360, go by 30s. Change it, make sure you go by 30s. Stop it before 360 and see what happens. Go after 360, it'll just sit there, it'll go there again. It'll go right over it. And if you need to, do a zoom 5, because it's a circle. So go to your window, you're probably still at 180. Yeah. But I like these because it really makes sense in your windows. Like when we do a line, you know, and we convert it to a parabola or a line, your window doesn't make as much sense. Yeah, because you're your T-set. Because remember, like in your clock, if you don't hit enough points, you're not going to go around and make a circle. It's going to hit this point, this point, this point. It's just going to connect them with a line. So you're making like whatever shape that happens to be. Sometimes if you set your mode different, it'll like squiggle the thing all over the place. If you put your mode in radians and do it, and you're working in degrees, it'll be weird. Okay, so now all we need to do is solve for these guys. So we're going to add 3, and then I'm going to divide by 3. Okay? I'm converting, I'm just solving in terms of your angle of your T. So I'm going to subtract 1 and divide by 3. That's your parametric, is your angle. Now, we've got a circle going on, and you never were able to graph your circle unless you use your parametrics. But to get back to a rectangular mode, we're just going to hook these guys back together. So again, the one form that you know is cosine squared plus sine squared equals 1. So you're going to take this guy. Just remember to square it. to square, take this guy. Remember to square it. So you're going to leave the top like this because that's where we usually see your pieces. We get a 9. We get a 9. So now to make the equation of a circle, this is like your special ellipse form, but it's a circle because these are equal. Just multiply through by 9. And there's the equation of your circle. Your center is negative 3, 1, which we wanted, and your radius is 3. So we're going from a parametric to a rectangular mode.
That makes it a circle?
Isn't that a circle?
Yeah, but I thought it was an ellipse.
Well, this is we moved it, we converted it to an ellipse format. But because these are both the same, our ellipse is a circle. It's a special kind of ellipse. So we're just going to multiply by the denominator and put it back to your circle form.
Like on the graph on the calculator, it doesn't look like a circle.
Change your t-step. Change your t-step, or do zoom 5. Do zoom 5 on it, and it should go back to the circle. Lily, first try zoom 5. Set your t-step at 30 and do zoom 5. Because your graphs on your calculators are a little bit exaggerated, it usually makes it look a little more oblong. Just do a zoom 5. It gives you more exact. So your parametrics allow you to graph these things because they're not functions. So we took it out of function mode and put it in parametric mode, which meant now your graph is going by an angle. As like picture going around the clock, because that's a circle. It's going like by angles all the way around. So your t-step is going to be in an angle. And play with that. Put your calculator in radians when you have this in degrees. See what that does. Change your t-step. Cut it short. Go over it. Play with those a little bit. So are we okay with these? Okay? They're not so bad. Just remember that. Keep that format handy. Otherwise, you're not going to be able to convert your circle. You have to put it in that first. Okay. That was it.